A bond's features affect the price-yield relationship. It's important to have a firm grasp of these effects, as they can be called, not to be taken by surprise when yields change, for example. Hi and welcome back. In the previous lesson, we studied the two components of a bond's price, flat price and accrued interest, that together make up what we calculate by discounting a bond's future cash flows, its coupons and its par value at maturity. That's commonly referred to as full price. By defining flat price and accrued interest, we also touched on evaluating a bond's price in between coupon dates. To do that, we introduced a more general equation to be used, one where we came across compounding for a fraction of a period. In this lesson, we're going to talk about a bond's price-yield relationship and its featuring elements: yield, coupon, convexity, and time to maturity, and the pull-to-par effect. The constant yield price trajectory as time passes by would be basically looking at our general equation for pricing a bond, as we've already seen in one of our first lessons. Just a quick heads up before we begin. Make sure you have the spreadsheet, the notes, and the slides ready to go. It's just that in this lesson, we're going to do that in a more structured way. More specifically, we're going to identify better the effect these features have on the price-yield relationship. In every time value calculation, using a higher discount rate lowers the present value for any future cash flow, and vice versa. There's an inverse relationship between a bond's price and its yield to maturity. We know that. Since the discount rate is the yield to maturity, a rising required rate of return for comparable bonds results in a lower present value of the future cash flows, and hence the bond price. This is the first thing we can say. Bond prices and their yields move in the opposite direction. And this is a relation we're going to use a lot in investment management. The coupon affects how much a bond's price will reflect changes for a given change in the yield for bonds with the same maturity. We're looking at the bond-yield relationship from two opposite perspectives. Let's call the first one the market perspective, where from the market price we extract the yield to maturity on the left, and the pricing perspective, the second one on the right, where given a discount rate we derive the bond price. By looking at our formula here, the smaller the coupon C, the larger the proportion of total cash flow 100 that occurs at maturity. Thus, discounting the last cash flow using the discount factor 1 plus r to the power of n amplifies the effect for a change in the discount rate of bonds with low coupons as opposed to bonds with higher coupons. This effect is magnified to the point of comparing a very low coupon bond with a much larger coupon bond. Nearly all the cash flows occur at maturity with a large payment in the end. The percentage price change is larger for the low coupon bond as opposed to the high coupon bond. This percentage change won't go unnoticed because we're going to see modified duration with as many details as possible about it before the end of this course. In this example here, we're comparing two identical bonds, except for the coupons. One is with a lower coupon, 1%, and the other has a higher coupon of 5%. Starting with a yield to maturity of 2%, the two bonds differ in prices. Of course, because they have the same yield to maturity. If we raise the yield to maturity to 3%, we notice that the one with the lower coupon decreases in price by more than the one with the higher coupon. I've demonstrated this in this sheet, where you can notice that for the bond with a 1% coupon, the last cash flow at maturity, at the 10th year, makes up for nearly 91% of all cash flows in present value. Whereas for the 5% coupon bond, the last cash flow at maturity accounts for about 68% of all cash flows in present value terms. Thus, when we value the two bonds using a higher discount rate, the one with the lower coupon has a price that decreases more because the effect of a higher required rate on the last cash flow is larger in relation to the early coupon payments. The yield also affects this relationship. As you can notice on the right side, if we start with two identical bonds with the exception of their yields, and we raise both by 1%, you can see that the one with the lower yield is more affected than the one with the higher yield. The direction in the yield change is also important. Notice what happens in the bottom left part of this sheet if I raise the yield to maturity from 3 to 4%. On the right column, the price decreases by nearly 9%. But if I lower the yield to maturity by the same amount, that is 1%, to 2%, the price goes up nearly 10%. This is what we already called convexity. In one of the more important lessons further into the course, we'll see a plot that shows this convex relationship. What's it mean? When market yields drop, the price soars at an increasing speed, whereas when yields rise, the price decreases by slowing down. And at last, the time to maturity affects a bond's price-yield relationship. I would add, obviously, but it's probably too early to say that. On the right side of the panel, we can see this as always by changing the yield to maturity of two bonds differing for their maturities. One is a 5-year bond, whilst the other is a 10-year bond. We notice that the one with the longer maturity is more affected by the change in its yield to maturity. Before continuing, let me show you that you can also print these sheets. I haven't told you yet, whenever you're making an Excel sheet, not just for presentation purposes, if you have to share it with someone else, whatever, make it beautiful so that it prints nicely. I try to show you what I mean. If you print this sheet as a PDF, for example, it prints nicely. It's also important for you because if you reuse these sheets, you can take notes on them, both in the PDF version and in the paper version. Doesn't really matter. If they're well organized, you read them gladly, willingly. The last topic we're going to cover in this lesson is that of the constant yield price trajectory. Bond prices keep changing even with their market discount rates remaining the same. Let's consider now these two bonds, A and B. They're identical, with the exception of their coupons and their price. Of course, they have the same yield. You see we're still using Excel's formula to price these bonds. I have left the equation we're using right now. We have no accrued interest here because we're photographing these bonds on coupon dates every year from when they have a time to maturity of 10 years until they mature. Their prices with 10 years before maturity are 83.78 and 132.44. If we move 1 year later on a settlement date of November 15th, 2023, bond A's price goes up to 85.13 and bond B's price decreases to 129.74. You can, anyways, see this price trend for both bonds in the chart I've already prepared, which is fed by the cells in the data tables underneath. We say that the price is pulled to par. For bond A, the price increases each year and approaches par value as maturity gets near. And conversely, for bond B, the price decreases as time passes and approaches par value near maturity. To keep the same yield, a discount bond's price increases as it nears maturity, whilst the premium bond's price decreases as it approaches maturity. Should we have a par bond that trades at par, you can probably imagine what would happen. Okay guys, before wrapping this up, I would like to highlight Excel's formula for present value. As we noted right from the beginning, a bond's price is the present value of the future cash flows. The formula I've left on the sheet is two things: the present value of the par value at maturity and the present value of an ordinary annuity. What's an ordinary annuity? It's a constant payment at the end of each period, periods with regular intervals for a finite amount of time. And the bond's price is basically the two combined: the present value of an ordinary annuity, whose payment is the periodic coupon, and the present value of a lump payment at maturity. Excel's present value formula does just that. It's the second formula. Why don't we use Excel's PV formula then? Because Excel's price formula does exactly what we did in a previous lesson. Remember our discussion about accrued interest and flat price? Excel's present value formula, as I've just demonstrated now, works just fine only on coupon dates. If we need to value the bond between coupon dates, we need to take into account what I called fractional discounting. However, Excel's present value formula is an asset in many other areas of finance. Some of them will be the topic of other lessons, some others won't. Don't forget to tackle the questions at the end of the lesson to strengthen your understanding. Also, make sure you've downloaded the slides, the spreadsheet, and the notes if you haven't already. They'll be really useful for your study and review. Okay guys, this wraps it up here, and I'll see you in the next lessons. The following section discusses yield and yield spread measures.